basically ready. Ignacio, do you want to kick off our panel?
Thanks, David. So it's my pleasure to introduce the panelists tonight or this morning. And so it's Chuang from MIT, John Martinis from University of California, Santa Barbara, John Preskill from Caltech, and Thomas Vidick also from Caltech. And so I will start with a general maybe statement about the topic of this workshop, namely quantum devices, simulation, supremacy, and optimization. So, I mean, there have been very interesting, let's say, results during the last year from the point of view of experiments and quantum computing. And so we have the first quantum computers that have demonstrated quantum supremacy. So my first question would be, would it be like a first step into building a scalable quantum computer, or is it more already that we have to enjoy that we have these NISQ devices and that we have to learn from them, and that maybe should pause and start just investigating what we can do with them? So maybe we can start with Ike.
Ignacio, that's a rhetorical question if I've ever heard one from you. I mean, John Martinez should really respond to whether we have a real quantum computer or not, but clearly we don't have a useful quantum computer. I don't think anybody will disagree with the fact that our current quantum computers are not economically useful. They don't yield anything of economic value. Now, whether they're scientifically interesting or not, it's a completely different matter. Clearly, these machines in different contexts are allowing us to do precision measurements that we could not have done a number of years ago. And I think that's very exciting for physics, but it's not quite so exciting enough for quantum computing.
John?
Well, I think you framed the question as, is there a trade-off between using the existing technology to seek interesting applications or pushing ahead towards more scalable devices? Of course, I want to do both. On the algorithmic side, we're now entering this era of quantum heuristics where we don't really have a very firm basis for expecting speed ups for problems we care about in the near term, but it's very important and instructive to try and to have a dialogue between the computer scientists and the algorithmists and potential users. Part of the challenging from a theory, what's challenging from a theory point of view is that we want to understand better the effect of noise on computational power. And from a complexity theory point of view, that's a somewhat unusual question because we don't want to consider asymptotically large depth. If we have some fixed error rate and width, then there's some optimal depth where it becomes maximally hard to simulate classically. And that means we're really talking about relatively low depth circuits and trying to understand how powerful they are. And we heard a lot of interesting results about that at this meeting from Aram and Sergey and Robert and Pfefferman. And so that's an important direction for the theory community to keep pressing on. And as far as fault tolerance is concerned, I think it's really important, and it's going to be a lot of fun and really interesting to see how successfully we can use error correction to make a stable quantum memory in the near term and on a small scale do fault tolerant gates. We'd like to see whether methods like randomized compiling are effective in real devices, whether we can characterize noise well enough to predict how well fault tolerant methods will perform, like Joel Wallman talked about in his talk. And, you know, that's, we can't leave that behind because it's so important for the future of the field.
Thank you, John. So John Martinez?
Yes, thank you. I'll slightly disagree with Ike Chuang in the sense that the quantum supremacy experiment was economically useful because we convinced Google executives that this wasn't some physics pipe dream, but actually might work, and thus they supported the quantum group much better. And I think it was very important to show that the basic physics worked even at a large scale of, effective parallel computation. And I think there's going to be more and more interest in this from, let's say, a Silicon Valley and other kind of views that this really may work from an engineering point of view, and they don't have to take the word of physicists anymore. I think that's important. One of the things I'd like to talk about is going beyond quantum supremacy. I started thinking about how we have to scale up. Of course, the big issue is getting the errors down to about 0.1%, and maybe few of our qubits are close to that, but clearly there needs to be work there. But what happened over last summer is I figured out a pathway to scale to, say, 100,000 or 1 million qubits, and then over the year I was actually solving some technical problems to get there. So I think there's a pathway to get there. When I say pathway, I don't mean 100% sure we're going to get there, but I could outline exactly what you need to do. And what I'm doing now is taking my knowledge from that, and I want to go look at other qubit technologies and see if there are other similar pathways where you really know what to do, and look at that seriously. So for me, it's an interesting time to look at it. Clearly, though, we have to make lower error qubits in order to do error correction and potentially to do NISQ. The numbers there are maybe 10 to minus 3 to 10 to minus 4 errors that you're going to need. But we have to keep working on it.
Thomas?
Sorry, you're asking me if we're going
Yes.
to build fault-tolerant quantum computers soon?
No. So what is your view? The first statement, and also about a little bit. So what is so the moment we have this NISQ, so and there is this perspective to building this scalable quantum computer. So how do you see the situation? What are your interests, or more the interesting from the computer science community?
I think from the point of view of computer science, we're waiting a little bit. So I'd kind of agree with Sean Preskill that the devices that we have now are not that interesting from a computer science point of view. There's maybe the number of qubits is scaling up and you can do these supremacy experiments, but the level of noise that we're seeing is way beyond anything that could be useful from an algorithmic point of view. So I think my perspective is that I find the proof of principle is interesting, but from my point of view, I still have 5 or at the minimum 5 years to go before there's anything to, probably more like 10 years, anything to play with.
Okay, so now I'm going to launch some questions. So whoever wants to answer, just start speaking. So the first is, do you think that is it important to further improve the rigor of supremacy achievements?
Sorry, I didn't get that. You said to improve the what?
To improve the rigor of supremacy achievements.
Of course it is. I mean, actually, one of the most interesting things I did in the last few weeks was to read the old papers of Shafi, Goldwasser, and Micheli, and Rivest. And in fact, they were investigating their own versions of supremacy years ago for signatures and cryptography. And this was supremacy of a computational complexity nature. And that was remarkably productive for today's society. And so if we have such rigorous bounds on quantum computation or hybrid of quantum and classical or other scenarios, it can be nothing but very interesting and fundamentally useful for us in the future. I think Thomas might agree with that.
Actually, I'm not sure. So I don't know exactly what you're referring to in terms of their work. I find the question of, because the rigor of the supremacy experiments is a little bit, it's kind of almost a self-defeating statement, because you're trying to prove rigorously some finite size demonstration. And so I think some of the work that has gone into that has been interesting from the point of view of complexity theory, average case hardness, understanding the role of noise. I think all of these are interesting questions. But fundamentally, I don't think that it's vital or crucial that we have a supremacy experiment that is fully rigorous. Maybe just because that's impossible, and by the time we get there, we'll be doing more interesting things. We'll be running algorithms, we'll be having interactive protocols, we'll be doing maybe quantum cryptography, we'll be doing actual simulations. And so the question of supremacy will be moot. So I think it's like starting the question theoretically is definitely leading to a lot of interesting work, but I don't think it's a crucial target in itself to have something that's fully rigorous.
I think it's important not just for validating supremacy per se, but because it, because of what comes out of it, because of the questions that the theory community addresses as a result, and coming up with better ways to validate that a quantum computer is performing the way we want it to is certainly important for the field. And like I said earlier, we really want to be able to say more firm things about the computational value of a device that's noisy. And, supremacy has provided an invitation to investigate those issues more seriously.
Yeah, thank you, John. I appreciate that. Yeah, and we're looking forward to people, looking at our experiment, looking at other things more deeply. I kind of think that the concept of looking at complexity, computational complexity of a problem is quite an interesting idea, and which is of course something we did for the quantum supremacy experiment. And I'll just throw out an idea that kind of I think about, I don't know if it's correct, but thinking about quantum complexity is way more interesting than thinking about quantum entanglement. I understand quantum entanglement is very important for quantum computing and the like, but maybe we're at the point now where things are complicated enough and big enough and systems are complicated that complexity, computational complexity is maybe something we should be looking more and more into. Just an idea.
I want to continue this for a second, if I may, Ignacio, because perhaps the difference between Thomas and I might be the definition of rigor. And what I'm interpreting your intent of rigor is understanding the clarity of the relationship of the parties and how the protocol is structured, not knowing a precise number of where you can say there is going to be supremacy or not supremacy. And maybe here's an example. So in these old papers by Goldwasser, Michele Rivest, and by Andrew Yao, I was really enjoying the Yao 70s papers when he was at Berkeley. Was he a student then? But he had, and they came up with rigor about the relationship between the roles of the people and the rigor of understanding how the protocols interfaced. And here's my example. Today we have two very different kinds of protocols, one using trapdoor claw-free functions, and another one using rigidity of magic square protocols. One of them certifies quantumness in saying that the two participants have a shared entanglement. The other certifies the quantumness in the ability to form a unitary transform. And yet both are certifying quantumness, and something is strange about having two different ways of doing it. Maybe they're related. Maybe fundamentally what we need in order to rigorously understand what's happening is to say, realize that, and this is an idea I'm toying with, it may not be true, but this illustrates, I hope, where there's freedom, that in a world of free teleportation, let's say, we know that we can turn states into gates and vice versa. And so maybe TCFs and the rigidity of magic squares turn into each other with that kind of a relative oracle.
Yeah, so if you formulate it this way, then I definitely have to agree. So I do find these questions interesting. They're questions about what are the minimal assumptions that you need to put in your system or the interaction that you have with it in order to gain some kind of leverage about or some kind of information about the results and how they have been obtained. And I think it's true that these are probing pretty deep into what's special about quantum mechanics and the devices that we're building. And it's true that we have, it's interesting what you're saying, and there's these few different frameworks that rely on a few different types of assumptions and that provide somewhat incomparable results. Yeah.
Okay, thank you. So maybe let's move on. So a question for, I think that for John Preskill is, will we learn some fundamental physics with NISQ machines? Is there any hope or?
And learn anything about what, sorry?
Fundamental physics.
Oh, fundamental physics. Eventually, I'm sure we will. I'm sure we will. But maybe you're asking about how long it's going to take.
So maybe can you elaborate on why do you think that it will?
Oh, well, okay. Well, the thing that interests me the most is the potential of getting insight into quantum gravity from quantum computation. That's not necessarily something we can do in the NISQ era unless we're really lucky, but it's not a ridiculous idea, because thanks to the string theorists who developed the idea of, they call ADS-CFT duality, we understand that full quantum theory of gravity has an alternative description which doesn't involve gravity at all, which we can simulate, we hope eventually, using quantum platforms. And what's kind of exciting is that recently we've seen that that type of duality can apply to quite simple systems, like what people call the SYK model. The K, of course, stands for Kitaev, which is really just a system of fermion modes interacting without any geometric locality constraints, but has a very nice geometrical description in terms of a black hole. What worries me about doing things like that in the NISQ era is the things we're interested in are probably very noise sensitive in the dual description. So I'm not sure how robust they'll be in real experiments. But what's kind of cool is that we've been seeing you can kind of turn things around, and phenomena which look very complicated to understand from the quantum platform point of view can be simpler to understand conceptually from the gravitational point of view. So some version of teleportation that involves a complicated scrambling phenomenon and unscrambling has a very natural description in terms of information propagating through a traversable wormhole. And I think experimentally exploring that kind of thing will give us powerful tools for understanding complex quantum phenomena, and will eventually teach us things about quantum gravity, and we'll be able to, with quantum computers, simulate non-perturbative effects that are probably too hard to simulate otherwise. But there's a very interesting cautionary note, which is an important contribution from the CS community, this recent work by Bolin, Pfefferman, and Vazirani, where they pointed out that the dictionary relating the gravitational and non-gravitational descriptions might, for some purposes, be computationally complex. Things we'd really like to know, like what's going inside of black holes, like at the singularity, might be very hard to access because of a complexity barrier in terms of the alternative non-gravitational description. And that's an important thing to clarify, where I think the computer scientists could really make a contribution.
Okay, thank you.
I wanted to mention that the quantum supremacy experiment shows that quantum mechanics still works at a Hilbert space of 10 to the 16, which is about 10 to the 13 times bigger than we ever knew before. So, you know, physics is always pushing the frontier of where we know physics can be applied. And certainly everyone thought that quantum mechanics would work as we scale up. But I would say that's a piece of knowledge about nature and quantum mechanics that we gained recently. And I think it's important that it works if we want to all practically move together on this field. So I think that's the piece.
Okay.
I want to follow in John's same thread and observe, or try to observe on behalf of my colleagues in condensed matter physics, that not all fundamental physics is about high energy physics. With all due respect, John, maybe you could say that Anderson localization is fundamental. And one of the things that piques my interest, and this ties together with your comment, John, might be that we don't understand noisy quantum systems. in a fundamental way. And I would really love to understand noisy quantum systems and have fundamental theorems about them, kind of like Anderson localization talks about that kind of a disordered system.
Yeah, and I kind of agree, because one of the things that actually surprised me a lot with the quantum supremacy data was how we could have a very simple noise description under, under the certain approximations or things that we did in the experiment. And I was kind of surprised that it worked so well, and think it would be good to think about that some more. And also in terms of Anderson localization, our group, I don't know if it's been published yet, did some nice experiments on that, as well as other groups. And it's a very nice piece of fundamental physics that quantum computers can investigate really well.
I don't want to get hung up on the word fundamental. Let's just say physics. And I think quantum platforms will be great tools for physics discovery, and that in the near term, probably the best potential is to see dynamical phenomena in many body systems that we haven't had a handle on before. And that can be pretty exciting. And I would emphasize that that doesn't necessarily mean circuit-based quantum computers. It could mean analog quantum simulators as well, where we're already seeing very interesting results in analog simulations of dynamics.
Actually, a very interesting analog simulation, an analog system, not for simulation. And I think you'd agree with this, both Johns, is precision measurement that probes fundamental physics. I don't mean to dwell on fundamental, but interesting physics like the change of variation of fundamental constants. Oh, darn it, I used the word again. But this is increasingly being made possible by the harnessing of entangled atomic systems that probe things due to the entanglement of degrees of freedom, and maybe even with molecules as well. I like to try to count that as quantum information science, especially these atomic clocks that use 2 ions and logic spectroscopy. And I bet that they will increasingly use ideas from computer science to make such fundamental, such measurements possible.
Well, as in other settings, the key thing is to understand what are really the classically hard things that we can learn from the quantum platforms that we don't have other ways of learning. And in the case of dynamics, that's not so obvious, because if you have systems that are disordered and highly localized, maybe they're not so entangled and not inaccessible classically. And when they're very strongly chaotic, they just converge to thermal equilibrium, and then it doesn't seem like anything interesting happens. But I think nature has great potential to reveal secrets as we study dynamics in a regime where we've never been able to before. We have to ask the right questions.
Actually, the trick is in the thing that you just said is not always true, of course. There are perhaps thermalized systems or systems that are thermalizing, which may nevertheless contain an enormous amount of entanglement, as long as you look at it in the right way. And maybe this is what is actually behind that slowing down behavior that happens that prevents thermalization, pre-thermalization behavior.
Experiments can help us understand those things.
Right.
Okay, wonderful. So let me remind the audience that you can use the Q&A knob that you have if you want to ask some questions as well. But in the meantime, let me ask the next question. And it's also about applications of these quantum computers. So can we expect for any fundamentally new algorithm or algorithmic approach? So maybe Thomas, can you start here?
So do you mean, can we expect to develop new quantum algorithms in the future? Not necessarily for the current.
Yeah, right.
I think we can. I think there's sort of pessimistic or blasé view that says that Shor's algorithm is the only algorithm that we ever discovered. I think that's very wrong. I think I would think that quantum algorithms is still a field that's in its infancy. I expect that the new devices that are being built will be useful in developing quantum algorithms. So things like the QAOA algorithm that we heard a lot about. This is very poorly understood. Maybe it's a useful algorithm, maybe it's not. We'll learn that as we use it, and this might give us ideas as to how to analyze it. I think more broadly, for example, quantum approximation algorithms is something that's very not developed. I know barely any quantum algorithm that has approximation guarantees as opposed to an algorithm that returns an exact solution. In the field of classical algorithms, this is incredibly developed, and it only developed sort of at a late stage when people invented linear programming, semi-definite programming, and designed approximation algorithms based on those. So I think that's one possible direction where things would develop. But I think even for fundamental problems like crypto-motivated problems, lattices, I don't think, maybe 10 years of research in that direction is almost nothing given the complexity of the problem. So I do expect many discoveries in the next 10 years or so.
Well, I hope when we can really run quantum computers, that will stimulate new algorithmic discoveries that will certainly change the game.
Ignacio, I was smiling because I was wondering, in the early days of classical computers, a panel like this might have existed where you might have said, is there any hope now that we have discovered the greatest common divisor algorithm or more algorithms? And as you know, today, what has happened is the major classical computer algorithms are things like MapReduce and rank pruning, PageRank, and these completely changed the notion of what an algorithm was because it became distributed. There's so little work on distributed quantum algorithms today, and it's more like protocols and not just algorithms, because there are adversarial relationships that are extraordinarily rich that can be envisioned. Like one of the most important classical algorithms today is called the Paxos algorithm. And I know many of us know this one. We use it daily. It's probably being used for the underlying database that makes possible the synchronization of this Zoom system. And what is quantum Paxos? These are really beautiful questions that still lie open to be answered.
I could read a question from the attendees from Anonymous, but I think an interesting thing to talk about. Do you, I think the you perhaps means all panelists, perhaps have any thoughts or beliefs on the future ability of measurement-based or cluster state quantum computation to compete with the more traditional approaches that are dominant currently? Who's interested in that?
I'll just make a comment. I think that there's been a lot of investment in photonic quantum computing, which I assume is along these ideas. And I would like, in fact, that there's a big part of the algorithm measuring the quantum states, maybe not quite what you're talking about, but what I don't understand is, I don't really understand the algorithm and the limits of how good all your measurements and all the elements has to be in that. Maybe I just need to sit down and figure out that. But part of it is really understanding the system requirements for these different proposals.
Yeah, I agree with John. I think the right computational model to think about depends on the features of our hardware. And if, for example, we have a device where we can make cluster states of many photons and by measuring them do a computation, then that's going to be a powerful approach. It won't be the best way necessarily with some other hardware platform.
I will pile on and agree with both Johns. It's hard to disagree with John squared, but it's kind of like measurement-based quantum computing or cluster computing is an extremal point because it talks about using only measurements, but it would be very, very interesting to come up with a rich variety, which uses a limited set of measurements together with a limited set of noisy gates. And we don't know these kinds of trade-offs, but on behalf of computer science, let me also point out that one of the most important things about measurement-based quantum computing is Urmila Madhav's beautiful work, where she bootstrapped based on that and TCFs to come up with these extraordinary proofs about fully homomorphic quantum encryption. And maybe the underlying concepts of teleporting gates is going to arise over and over again, irregardless of whether you call it cluster-based computing or not, and in many different protocols.
Okay, thanks. So I have a question for John Martinez. And so you mentioned that there seems to be a path, at least that you found a path for scalability of this, of a quantum computer. So is it a question now of money, of investment, or I mean, let's have like an ITER or a CERN for quantum computing. Let's try all of us to work together on that, or it requires some time and different places competing with each other. So what is the model that you have in mind for that?
Yeah, the most important part to the path is actually figuring out how to get the gate errors to about the 0.1%. You know, initially, if you're at 0.2 or 0.3, that's fine. And then you just make it better over time. That's fine. And the nice thing about the quantum supremacy experiment is you build enough grid of qubits so that you know that you're testing it in a realistic way. It's very easy to test qubits in some simplified way and think you're doing fine. When you scale up, it doesn't work. When I set a path, I mean, it's like you could figure out all the technologies you had to build. And in fact, you know, over December, I figured out one important thing. And it's just a matter of getting everyone together in the right environment to put that together. And yeah, yeah, maybe I better won't say more than that.
Okay. Sure. So maybe a related question, but now from the more theoretical point of view. So do you think that in the case of quantum error correction, so we have already reached the best that we have, or there is a lot of room for improvement in terms of overhead thresholds and so on? So maybe
in terms of the theory, you're saying?
Theory. Yeah, now the theory. Yeah, I'm asking about the theory, right?
Yeah, good question.
We don't even know what the threshold for fault-tolerant classical computing is today. So
Okay.
It's very hard to say we know the end of the story for fault-tolerant quantum computation. But I bet John is rearing to answer this question. So go for it, John.
Oh, I'm just saying the nice thing is you can do experiments and measure how much better things get as you build it bigger and bigger. And you can measure it in space and time and do that. So, you know, we can take the existing models and see how we're doing. And, you know, we're hoping that people come up with even better ideas or, you know, maybe more clever ways to do the architecture that will help us.
So John, so you're saying that it's a question of working together, experimentalists and theorists, in order to improve that?
Yeah, that would be very good. And I think, you know, I mentioned this earlier that, you know, once you, and maybe John, that, you know, once you kind of understand what your error models are and what's going on, you can then figure out how to build the system properly or maybe apply the error correction. So fortunately, we know enough now to, you know, move ahead in a definite direction and make progress and validate if we're doing properly. But, you know, again, as you get data, people should keep thinking about how to make it better. And, you know, just for example, the decoding algorithm for the surface code is, you know, that's a pretty hard thing to do to get that to work fast. And I think there's a, you know, I think it could be a big effort for people, multiple groups to work on that. I'm just on that piece of software to do it efficiently. You know, for superconducting qubits, you're talking about a supercomputer size decoding classical computer to run alongside your quantum computer. Not quite the size of Summit, but, you know, a big computer. And I think there could be more effort and more work to solve that problem, which would be a good computer science and physics problem.
Well, you know, we've all seen the discouraging overhead estimates. Even if we have a gate error rate of 10 to the minus 3, came up in Alexander's talk today. Actually, work by Ike and his collaborators, and Easton and Cannell and others, emphasize that there's kind of an obstacle to getting a universal set of gates that are fault tolerant for quantum code. There have been a lot of interesting new ideas in the last couple of years about how to achieve universality. The traditional answer has been magic state distillation. There are other ideas, none of them have been game changers. I think there may be an opportunity for theorists there that we don't really have a very systematic way of thinking about these things, understanding the different possible ways of getting a universal fault tolerance set. And if we had more of a better theoretical framework, that might suggest new ideas. And then, of course, I also agree with the philosophy Alex Zond had in his talk, that if we can, put in some protection at the device level, perhaps devices with highly biased noise, we can take advantage of that. And that might allow us to get to low logical error rates sooner.
I also think that if you start having experiments, starting to do more and more serious error correction, then that'll encourage computer scientists and physicists to look deeper at it, because they'll see that their ideas can be applied in a reasonable amount of time. So we have to catch up some, that's for sure.
Ignacio, I'd like to highlight a comment by Eddie Farhi and use that to maybe partially respond to your last question, and then tie into what Martinis just proposed, that there needs to be a greater effort. Eddie exhorts us by saying you should encourage people to work on quantum approximate optimization algorithms where we have taken first steps. And there's a very nice sense here that maybe what we need to do is to encourage exploration with a metric that lets us measure progress. And in the computer science community, this is now done by having competitions, for example, for image search, labeling, machine learning, in places where we don't actually have any proofs of any performance bounds on algorithms. We could have the same kind of thing. We're almost reaching at the stage at which maybe some quantum computers could be used, or maybe some theoretical models could be employed to allow there to be a leaderboard of scores of approaches that solve interesting, relevant problems. John, maybe this would address some of the ideas that both of you raised.
Well, one thing I'd say about, go ahead, John.
Yes, I agree. Of course, you have to be careful what your metrics are, and think about that carefully. But as you have more and more experiments, and you're running algorithms, even in the NISQ era, whatever, then it becomes a little bit more clear what the proper metrics are. But it's good to approach it. When you write metrics for your laptop, what is it? There's hundreds or thousands of metrics on different programs to run, and people kind of take an average that. So we have to get started on that.
Well, just a quick comment about QAOA and other variational approaches. You don't necessarily need universal control to do it in an interesting way. If you have a device like an ion trap or a neutral atom system, which has its own native Hamiltonian, which is tunable, then that might give you access to an interesting set of variational states. So that's another approach that we're going to be exploring, I hope, in the next few years.
Yeah, and Misha Lukin's beautiful presentation highlighted how this is done for Rydberg atoms. And so it may portend much tighter involvement of theory with physical evolution of a nature which haven't actually seen in classical computation for a long time. There used to be this notion that we would manipulate analog degrees of freedom to do classical computation. Of course, all that has gone away. So maybe part of this will be both the classical dynamics and the quantum dynamics of these systems that you mentioned, John.
Well, in the long run, digital, is more scalable, and it's more flexible, and the Hamiltonians you can simulate, and the state preparations you can do. But in the near term, I think analog is very promising to explore.
Yeah, vacuum tube computers lasted and helped the United States and the world for many years.
There's a question from Debbie Lung. She asks, now that experiments have advanced significantly recently, do we have some ideas how the physical noise may change as we scale up the computation? So that's definitely a physics question. Maybe more unitary and less stochastic. I don't know. What do you guys think?
Well, I'm just going to say, in the quantum supremacy experiment, we were concerned about this. And by, you know, engineering things very, very carefully in terms of crosstalk and whatever, in the end, our noise model was what we measured with 1 or 2 qubits and kind of, you know, understood on that. So I was kind of pleasantly surprised that there wasn't any obvious new physics going on. Of course, we have to continue to look for that, but that's good news. But, you know, you're gonna have to look at each system to see if something unexpected appears. And of course, once you start doing error correction and you can look for multi-order errors, which are not really seen in the quantum supremacy experiment, you know, you have to check for that. And again, we just have to proceed with these things.
Well, as John said, the Google experiment admits a very simple model of how the you know, circuit fidelity scales with the circuit size. And maybe the part of the reason for that is that those random circuits were such good scramblers of quantum information, which turn the noise into something very simple. And we don't know how well that will apply to more structured algorithms. So that'll be an interesting thing to learn about.
Yeah, and you know, my thought is you can always apply kind of spin echoing in kind of randomized spin echoing, the generalization of spin echoing, to mitigate some of the correlated errors you might see. And that's certainly what the quantum supremacy does, and what you would do for a full error-corrected quantum computer. It's using lock-in techniques, essentially. This is a very well-known experimental idea. But we have to see if those work. We have to see if there's new mechanisms, subtle things going on. So yeah, there's a lot of research to do there to understand. It's really a good question, important thing to do.
I like, Debbie, your question a lot. And actually, I want to turn it around and suggest a challenge to Martinis, which is, could you then, instead of using random Paulis and so forth to get rid of the noise or mitigate it, reconstruct your algorithm and circuit to accentuate it so that you can figure out exactly what kind of correlated noise might exist, because there might be unexpected and very interesting correlated noises.
And in fact, when we go to tune up the devices, you run sequences to accentuate noise to see what's going on, and then you can tune in your control parameters to do that. So yes, for example, when you have control errors, you can really minimize your control errors by accentuating.
Right. This is great. So
yeah,
Debbie,
we play those tricks.
John, what Debbie is telling you is that maybe you should investigate your noise much more closely. It's not the first time a Nobel Prize has been hidden in the noise.
Yes, that's great. And yeah, I agree. And I think what'll be interesting is when the Google team, you know, gets the device out on the cloud, then people can propose to do things. And it would be very interesting to get many, many people thinking about that and learn from that. So that's key.
So this is getting really interesting. We're way over time as compared to the program. So I think that maybe it's time to wrap up. So maybe I want to hear a statement about the meeting, about the progress, or about whatever you have in mind from each of you. And then I think that we will close the session. So we can start alphabetically, maybe with Ike.
Yeah, just one very brief comment. I'm ever so grateful to the Simons Institute for bringing this together, because one of the neatest things I found was this interface between computer science and physicists being really celebrated by bringing both crowds together. And many of these quantum meetings, I'm finding one or the other and not the combination. Maybe it was an accident of having the lattice people at the same time, but it was truly nice to see that. And I think that that one of the weakest wheels in the quantum computing machinery right now is getting computer science spun up to be really truly invested in this whole process. So thank you to the Simons Institute, and I hope many other folks also share this perspective.
I think so. I think that everybody shares that thought. So the next one, maybe John Martinez.
I was just going to say, I think things are quite vibrant and exciting right now. And we're just going to keep on going for the next 5 or 10 years doing great experiments. And let's just, you know, see where we go here. It's really in some sense opening up or continuing to be a very vibrant field.
John Preskill?
Well, just building on what Ike said, the Simons Institute is a great gift to the theory community. And part of what makes it so valuable is it has a very high profile online. And I, as someone who had planned to come to Berkeley, but whose plans were dashed, like I'm sure many others, have very much appreciated being able to follow what's going on throughout the program through that online presence. And I think part of the legacy of this program can be showing how successful online events can be. This is the second workshop that transitioned to an all Zoom format, and those were two very successful workshops. And so I'm grateful for all involved who made that happen.
Yeah, I think that all of us agree with that as well. Thomas?
Well, maybe I'll flip around John and Ike's comments and say thank you to all the physicists who joined us at the Simons for this semester and agreed to engage with the computer scientists and share their ideas. This is particularly true for this last workshop. So I think we've received great response, and it's great to indeed have the Simons Institute help us attract people and come and give talks. So since I'm last, maybe I'll also thank a lot of the organizers. So first, the organizers of this workshop. So Ignacio, David, and Barbara, thanks a lot for putting this together in spite of the difficult circumstances and getting such a great lineup of speakers. We had a very, very large attendance, I think, this week. It's impressive. The talks had anywhere between 100 and 200 participants logged in, and many hundreds more watching the stream and then offline. So thanks a lot to the organizers and the speakers. I'll also thank organizers of the other workshops that we've had. So let me not name everyone, but thanks to everyone. Also the co-organizers of the whole semester. So Andrew Childs, Ignacio Sirac, and Umesh Vazirani, thanks a lot for helping or putting this together. And yeah, as Ike and John said already, thanks to the Simons Institute for hosting us for a great, if turbulent, semester. And thanks to the leadership, Peter Bartlett, Shafi Golwasser, all the way to the technical staff, Umid, who's still with us, and Ashley, who was a little bit ago, and all the others. So thanks, everyone.
Thank you very much. So thank all the panelists, and it was an enjoyable evening here in Europe, maybe morning there in the US. So maybe I pass the word to David to say the last comments. David?
Oh, well, I don't have so much. I would have loved to have hogged the entire panel discussion and asked my own questions. You know, how the million qubits are really going to work, and I always have my black hole questions for John Preskill, but we'll have to save that for another day. I'm glad that Umesh Vazirani still has his camera open so we can actually see what it looks like there in California. I feel a very strong sense of envy that I missed my 2 weeks in California. But anyway, thanks to all of you for your comments and for participating. And I think that's all I have to say. Barbara's the only one who hasn't had the last word. You want to say something, Barbara?
No,
you're muted.
I think we're going to sleep soon, right?
We're all in a little bit of Zoom fatigue.
I want to take a walk. Actually, I want to take an evening walk after this. It's
okay.
still light, so maybe I should do that. Yeah.
Mm-hmm. Okay.
Yeah, it was great. Should we do it again? Yeah.
All right. And Eddie Farhi says, enjoyed your remarks. Stay healthy. Eddie, bye. So good last word.
Yeah.
Okay.
Bye-bye.
Bye-bye.
Okay.
Bye. Thanks.
Bye-bye.
Bye, everybody.
Bye-bye.